Hello everyone. I'm Kai. I'm so excited to be here to share our journey of migrating a multi-platform game engine to Bazel. So we have a lot we want to share today, so let's just get it started. So I came from the Evil Echoes team. Evil Echoes is a space game developed by Netease. It's powered by our in-house engine named NeoX. So NeoX has a long history since 2009. And since last year, we decided to improve its build system. So Evil Echoes has a very small development team. We have only 20 developers joining the migration, and nearly only half of them were working with NeoX. This affects our migration in two ways. On one hand, we have limited resources. So as you can see, we had to do some pretty hacky stuff to work around some issues we encountered. But on the other hand, having a small development team means that we can easily adjust our workflow, which made our migration easier. So before Bazel, a full build of NeoX engine took us more than 20 minutes. If we updated some rendering-related code, which happens quite frequently in game development, the build time was 14 minutes. So as you can see, this greatly impacted our productivity. So we decided to find a new build system to improve it. Now, here are the challenges we faced. NeoX targets iOS, Android, and Windows platform. And we sometimes need to compile part of the engine on the server side, which is Linux. So that's 4 different target platforms. In order to build an iOS app, we need to use macOS plus Windows and Linux. That's 3 different host platforms. On the language side, NeoX mainly uses C++, so we have more than around 2 million lines of C++ code. We have very few Java code to interact with Android system, and likewise, we have some Objective-C code to interact with the iOS system. Now, software development is very complicated, so we need the profile and the debug tools provided by IDEs like Android Studio, Xcode, and Visual Studio, especially when you target the mobile platforms. So we need the build system can be integrated into all these 3 IDEs. So with all these requirements combined, it looked like an impossible task. So imagine how excited we were when we found out Bazel's homepage. And it's almost as if it's tailor-made for us. And we were very pleased to find out Bazel lived up to all its promises. So in February last year, we wrote our first Bazel rule. The first fully Bazel build version took us 3 months. Then we spent another 2 months to add the IDE integration and remote cache support. We added the remote execution support for iOS and Android build with the build farm in the following months. In October last year, we finally released our first Bazel build version to the players. And we finally got some time to work on the custom remote worker for the Windows platform. I will explain it later. And finally, at the end of the last year, we had remote execution set up for all 4 targeted platforms with build bar. Now, after moved to Bazel, the Windows full build time dropped dramatically from 27 minutes to 4 minutes. For iOS and Android, it's even faster with 2.5 minutes. So this sounds like an unfair comparison because there actually low build happened with all the remote cache hitting. But this did save us a lot of development time for real, especially for our CI jobs. Now, when we do update the rendering code, the increment build time dropped from 40 minutes to 4 minutes. And I need to mention that this build was running on a remote cluster composed of 3 macMinis. So if we throw more macMinis into the cluster, we can further cut down the build time, but that's with the hardware we got for now, and we are quite happy with it. So let's start the migration. Before Bazel, NeoX uses cmake to generate Android Studio, Xcode, and the Visual Studio projects to build for each target platform. all the C++ dependencies are managed by Colon. It's a very simple setup. So we want to migrate seamlessly from cmake-based solution to Bazel without stopping the normal development. So we decided to move the cmake library targets one by one to Bazel. So after we moved a library to Bazel, we use the cmake import library target to import it back into the cmake generated project. This library target is further depends on another custom target, which is responsible for calling the Bazel build command. So in this way, we get a hybrid build system. So the normal developers still use the cmake to generate the projects, but some of the libraries are already built with Bazel. Now, Bazel already also need to share the third-party dependencies managed by Colon. Luckily, there was already a tool for this. It's called the Colon Bazel generator. It's available since Colon 1.61. Now, the generator works like this. So if you execute the Colon install command to install all the third-party dependencies, the client will first read the Colon profile from your project, reload all the dependencies, download all the required libraries from the server, save them on the disk cache. Then it asks the Bazel generator to analyze those libraries and generate the Bazel build files automatically. The Bazel generator will also create a macro to load all the Colon dependencies. So it uses the local repository rule to load all the cache from the load all the libraries from the local Colon cache. This is the build file generated by the Bazel generator. It's actually very simple. Now, the generator was in experimental stage back then, but it was generally usable. We have to fix a few minor issues. The most issue we encountered are due to incorrectly packed libraries. The real issue was that we had to call the Colon install command before Bazel build if we are not sure any of the third-party dependencies have been updated. But we really hope all our developers can build the engine with a single Bazel build command. So we decided to replace the local repository with HTTP archive. So when generating the macro, instead of using local repository, we use HTTP archive to download the library files from a Colon server directly. In this way, the macro and the build files all don't contain any local passes, so we can commit to the repository. Other developers can just use a single Bazel build command to build the whole engine. Now, we still need to call the Colon install command when we update the third-party dependencies. Now, I think we can write a repo role for this. So we can write a repo role to execute the Colon install command during the build in Bazel, something like this. But we have limited resource and we don't update our dependencies frequently. So the current solution is okay for us. Now, after we finished Bazel, the integration with Colon and cmake, the migration actually went pretty well. Most of the issues we encountered are due to NeoX itself, and mainly fall into three categories. The first one is the include path that allows starting from the root of the repository. So we can't get away with this by abusing the include attribute from the CC library, but we really want to take the chance to make our code more correct. So we decided to write a Python script to fix all the include passes. So first, we need to generate the compilation database for NeoX project. That's all the tools we used for three target platforms. Now we got the compilation database. We can extract all the included directories for each source files. Now we can try to locate all the included header files in those directories and restore the correct full path. Now, this solution is not perfect. We still may get some incorrectly included paths, but those are quite a few. So we just manually fixed what's left. The second issue is missing the dependency declaration in the cmake project. So this kind of issue is very easy to fix. We just add them back in the Bazel build file, but it will lead to the trickiest problem we have to solve: circular dependencies. So normally, if we want to break circular dependencies, we have to divide some large libraries. So for example, if library X and Y depends on each other, normally X is dependent upon a very small subset of Y. So we can move that subset from Y into another new library Z. Now, X and Y can both depend on library Z, and now library Y can safely depend on library X. But in practice, sometimes it's very difficult to move the subset out of the large library without significantly changing our code. But we were impatient. We don't want to hold our migration too long, so we decided to create some fake header ending files. So we move the header files from the library Y, but we keep the source files in library Y. Now, the library X built with the library Z cannot be used alone. That's why we call it fake header ending names. It has to be linked together with the library Y, but that's totally okay for migration. We still recommend you to fix this kind of issue after you finish the migration. Sadly, in the later stage, we found that include what you use can help a lot in this situation. We found out that many of the circular dependencies are false dependencies caused by developers copying includes from one source file to another source file. So after we remove those includes, with include what you use, the circular dependencies are already fixed. Besides the above issues, we also changed our linking model a little. For Android build, we switched to static linking for lab C++. Now, in order to use dynamic linking to C++, we need to copy the lab C++ shared SO file into the APK. Currently, Rose Android don't do this, so we cannot use dynamic linking here, but I think this can be easily implemented after we fully move the Rose Android to Starlock. Also, we switched to static linking to most of our labs on the Windows platform, or more correctly with MSVC. So generating and linking with DL needs some special care with Bazel, and we want to keep all the roles consistent for all our platforms, and we are okay with static linking, so we switched most of the libraries to static linking, and in some security-related library are remained dynamic linking. But this did cause the linking time increased to 2 minutes. So recently we were thinking about switch back to dynamic linking, maybe with the help of macOS. After we could build NeoX entirely with Bazel, we started to add an IDE integration. For Android Studio, we use the official Bazel for Intelligent plugin. We don't use Android Studio heavily, but for our use cases, this plugin works quite well. So in order to debug a C++ code, we need to enable a special compilation flag. This flag is also required for you to debug a remote cached library. So I will talk about it later. For Xcode, we started with 2C and then later switched to Rose Xcode project. After 2C was deprecated, both of these tools works out of the box for our use cases. For VS, we found a tool named Lavender. Lavender can be used to generate a Visual Studio project from a Bazel project. It's no longer maintained anymore, but its code has solid foundation. We managed to fork it and update it to work in a short time. So we open sourced it here. This tool made a lot of assumptions about the NeoX project, so it may not work out of the box for your project, but you can take it as an implementation reference. But while adding the IDE integration, we were also working on adding remote cache support. If you enable sandboxing for your build, enabling remote cache should be quite easy and straightforward. So we highly recommend you enable sandboxing, at least for your CI builds. We started with Bazel Remote. It's very easy to set up, so very suitable for first trying the remote cache. Now, this is the C++ compilation flag we needed, the debugger compilation directory. Basically, it will convert the absolute path in the debug symbols to relative ones that are relative to the repository. In this way, your debugger can find the source files correctly. For iOS, you will need an additional linker flag named also prefix, which basically does a similar thing. And the toolchain generated by Rose Apple already have 2 features defined for this, so you can just enable them. Now, enable remote cache on Windows is much trickier. So first, we failed to find some compilation flag, like debugger compilation directory. So we have to turn off remote cache for link actions. So all the link actions are executed locally. We also need to change the debugger information format to the old style, which means Visual Studio will store the debugger information in the object files. But the most interesting issue we encountered is that enable strict action flag is not enabled for us to share the remote cache across the whole team. So when built with VS, Bazel will use the script provided by VS to get all the required environments. As you can see, those paths contain the installation path of the Visual Studio. So if 2 developers install Visual Studio at 2 different locations, you won't be able to share the cache between each other. We are a small team, so the fix is very easy. We just require all the developers to install Visual Studio at the default location. But even after that, we found that with some developers still failed to share the remote cache from other developers. It turns out the values returned by the script are based on which components of the Visual Studio you installed. So, for example, this developer also installed the .NET SDK, and the path related to .NET SDK is also in the path, which is unused for C++ toolchain, but it will make this developer fail to share cache with other developers. Now requires all the developers to install exactly the same components of Visual Studio are much harder, we think, because sometimes developers may want to experiment with some new language for some special task. So we decided to manually remove all the unneeded values from the toolchain. Then we copy and commit the toolchain into our directory, a repository, and ask Bazel to build a Windows version with it. Now, in this way, we can finally share remote cache among our whole team. Of course, this can be handled better. Rose Android NDK and Rose Apple actually demonstrated 2 different ways for this. So Rose Android NDK use a repo rule to map the local installed toolchain into external repositories. This is the preferred way, I think, because in this way, your remote workers won't need to install the toolchain again. But it requires all the toolchain related files in a single root directory, which is not the case for Xcode and Visual Studio. On the other hand, Apple use the placeholder environments. So those in the toolchain, those environments variables will be replaced with the real ones provided by the Xcode local in the provider. Now, I think we can do the same thing for MSVC, but this requires modifying the Bazel core, so that's not ideal either. Now, the final piece of the puzzle is the remote execution. We started with build farm. Build farm is very easy to set up. We used it for our iOS and Android build for like 3 months. When we tried it on the Windows platform, we occasionally get some file system related issue. Our team is not familiar with Java, so we failed to identify the root cause. We had to switch to other remote server implementations. But you mainly work on Linux and macOS, build file is a great option. Later on, we tried build bar. There will be a talk dedicated to build bar tomorrow, so I won't go into too much detail here. Now, build bar has different kind of file system-based workers. For example, on Linux and macOS, it has virtual file system-based workers, which is super efficient. On Windows, it has native file system-based workers. Now, for large projects like NeoX, the native file system worker took too much time to prepare all the input trees, so we can't use it. Luckily, there is a very simple API defined between the build bus scheduler and the worker. There is only one gRPC call. This means we can easily implement our custom worker to work with the whole build bar cluster. That's what we did. So we open sourced the worker here, like the Lavender we open sourced. It made quite a lot of assumption about the NeoX project, so it may not work out of the box for you, but you can take it as an implementation reference. The worker is written with Python script. Now we learned from the build file to cache input trees instead of individual files across actions to construct a large input tree on Windows platform are quite expensive. Now, there is actually a very nice virtual file system API provided by Windows called Project FS. We always want to implement our worker with the Project FS, but we don't get the time, maybe in the future. And a special thanks to Edit Shorten. I don't know if you are here, you helped us a lot during the creation of the worker. Now we have workers running on both macOS and Windows. We need to match the build actions with the correct workers. This is the Bazel remote API has a plan for properties defined for this. So if we have a worker defined a property named host OS with the value macOS, and in the actions that also contains the host OS value set to macOS can be accepted by this worker. But we haven't moved to Bazel platforms yet. We have to wait those Android ADK, those Apple both move to Bazel platforms, which are already here recently. We are happy to see that. So instead, we use remote default execution properties to set the values. Now, the final piece of advice we have is that if you are just start to experiment with execution, remote execution, you can turn off remote strategy for all actions by default. In this way, if there is some actions in your build pipeline that are really hard to implement it for remote execution, it won't stop you from using remote execution to speed up the most expensive actions in your build. After that, you can slowly migrate your other actions to support remote execution. So that's it. After a year of work, we finally get our engine built with Bazel, with remote cache and remote execution support, fast and correct. Of course, we are not done with Bazel yet. In the future, we plan to move the resource cooking pipeline to Bazel. In a game engine, resource cooking pipeline means comparing shared code and compressed textures, which is perfect for Bazel. We want to move to Bazel mode and platforms API in the future. And we actually use Python a lot as a script language. We plan to implement aspect rules for MyPy checks. We already did this with our client ID checks. That's it. Thanks.
Did you set up, include what you use? Did you use the compilation databases that you had mentioned in a slide earlier?
Yeah, we use it in the compilation database. We hope to use aspect rule, but that's more, we have limited source. Okay.
Yeah, that's what I was hoping you did, and then open source there or something, but that's great. Thank you.
Yeah, thank you. Okay. That's it. We are good. Thanks.